This video is an introduction to logarithms.
We have been working with exponential relationships. Here's an example. We have 2 to the 5th equals 32. And we have some names for different parts of this. That 2, that is called our base. This 5 that's in the exponent, that's our exponent. And the 32 is our value. Typically what we've been doing is I give you the base and I give you the exponent, and then you have to figure out the value. So for instance, we might ask you to evaluate 2 to the 4th, and you know that that gives us 16. But what we're going to do it with logarithms is we're going to think about this in reverse. So instead of giving you the base and the exponent, I'm going to give you the base and the value. And you have to come up with what that exponent was. So for instance, if we know our base is 5 and our value is 25, we know our base here is 5, it's raised to some exponent, and we get 25. And we want to know, what is that exponent? Well, we know 5 squared is 25. So our answer here, our exponent, that's our answer, is 2. Here's another one. We know the base is 3, the value is 81, and we want to know what is that exponent. So what power of 3 gives us 81? So you might not just automatically know that answer. Let's think about what 81 is. 81 is 9 times 9, and each 9 is a pair of 3's. So 81 is actually 3 to the 4th. So 3 to the 4th is 81. So this means our answer here is 4. So what we're doing is we're doing these problems backwards from how we usually did them. And instead of evaluating exponentials, what we're doing is evaluating logs, or a logarithm. And a logarithm is really just an exponent. So even though it's got that weird word, you may not have heard that before, logarithm, all it is an exponent. And you guys are great at exponents. Let's look at this a little bit more in depth. If we have a log base b of x equals y, what that means is if we take this base here, that's our base, to the y, here's the y, that's our exponent, and we get this x, that's our value. So we're just answering that same exact question that we're working on. Remember in this example that we first did, we had 5 squared was 25. So that is written in this form. And what we want to do is we want to write that in log form, because it's easier to express what we're saying instead of saying, well, if my base is 5 and my value is 25, what is the power? This is a faster way to say it. If I want to take this and I want to rewrite it in log form, we've got log base 5 of 25 is 2. Here's the second one that we had. We had our base was 3, our value was 81, and we figured out 3 to the 4th was 81. And so writing this in log form, we have log base 3 of our 81, of our value, equals our exponent. Let's look at a few more examples. So in this next one, we have log base 5 of 1 over 125. So this one's a little bit harder than the ones we've been working on. The question we're being asked is, what power of 5 gives us 1 over 125? So the first thing to sort of look at is, what is that 125? Well, 125 is 5 times 25, and 25 is 5 times 5. So this is really 5 cubed. I need to get 5 cubed in the denominator here. So 5 to the what is 1 over 5 cubed. Well, we know that when we have a negative exponent, that just moves things down to the denominator. So we have 5 to the negative 3 actually gives us 1 over 125. So my answer here, the answer is that exponent. So the value of that log is negative 3, that exponent. So let's look at another one. So we're asking log base 9 of 3. So we want to know what power of 9 gives us 3. Some of you are probably going to think 1/3 of 9 gives us 3. But that's not going to work because 1/3 is not a power. We need it to be a power. Another relationship that we have that involves 9 and 3 is if we take the square root of 9, that gives me 3. And we can actually write square roots as powers. Remember, if we have a square root, that's like raising something to the 1/2 power. So 9 to the 1/2 gives us 3. And so now I know what power of 9 gives us 3. That's my answer here. The answer is your exponent. Last one. So we want to know what is log base 2 of 1. We're asking ourselves what power of 2 gives us 1. Well, 2 to the 0 gives us 1. So this exponent here, that's the value of my log. One important thing to note is when we're evaluating logs, the value of our base cannot be 1, and it always has to be greater than 0, just like with exponentials. Also, when we get a number here, this our value that we're looking at, that value has to be greater than 0. We can't take a number that is greater than 0, raise it to a power, and get something that's less than 0. So this has to be greater than 0. So our b cannot be 1, it has to be positive, and our x, the thing inside our log, has to be positive. So we wouldn't ever ask log base 2 of negative 7. This would be undefined because we can't take the log of a negative number. Oftentimes you'll see just plain log of a number, like log x, and this is what the log on your calculator is. That means log base 10. So if I were trying to figure out what log of 10,000 is, well, 10,000, that's 10 to the 4th. So log of 10,000 is going to be just 4. So now notice that this base here was dropped. There's no log base 10 there. So if there's no base, it's a common log, and you can assume, and the base is really 10. Another type of log is log base e. So remember, e is that number that's about 2.72, and it comes up in lots of applied problems, especially ones that are from nature. Let's look at this first one. Here it says natural log of square root of e. Now, when you look at this, it sort of looks like in, but it's not in. It's L for log, so it's natural log. So I tend to write those in the ln in cursive. If we're trying to evaluate natural log of square root of e, remember we're trying to figure out what power of e gives us square root of e, and well, e to the 1/2 gives us square root of e. This is 1/2. That's important fact there. One more important fact is when we're taking the natural log of e, this is just log base e of e. So we're asking ourselves what power of e gives us e? Well, just 1. So that's a fact that we use frequently later in this video. Since exponentials and logarithms are inverse operations, they undo each other, they are going to behave in similar ways. So if we look here, we can see that we have some exponential rules that we've used throughout algebra, and then the corresponding logarithm rule. When we've got things with the same base, and we're trying to combine them into just one power, what we do is we add those exponents. So if we have b to the m times b to the n, it's going to be b to the m plus n. And the same things happens here. So if we've got log base b of some product, a product, turns into a sum. When we're dividing things with the same base, we can combine them by subtracting. We've got the same thing with logs. If we're taking log of a quotient, we can break it apart by doing subtraction. And then when we are raising one power of b to another, what we do is we multiply. And that's the same thing here. If you're taking log base b of x to the r, we can take this r here and it can go from being in the exponent to being a coefficient. This rule turns out to be really handy, and it can solve a lot of problems with algebra for us. To restate what this says, it says we can take something that is in our exponent and we can rewrite it using that log so that it becomes a coefficient. Let's see how we would use our rules for logs to solve an exponential equation. So we're good at solving equations. We've solved lots of equations. However, this type of equation provides a different type of challenge because our variable, our x, is stuck up in the exponent. Our goal is to get, some value for x, but the problem is that x is stuck in the exponent. Well, the solution, use a logarithm. So what we're going to do is we are going to take the log of both sides of our equation, kind of like we take square root of both sides or we cube both sides. We're going to take the log of both sides. I start out with 2 to the negative 3x equals 12, and we're going to just log both sides. So the two types of logs that I tend to use is that common log, or I use that natural log. Let's go ahead and use common log this time. So what we're going to do is we're going to log both sides. So we're going to have log of 2 to the negative 3x equals log of 12. Now, sometimes people get confused that it's kind of like you're writing these three letters log out in front. What you're doing is you're taking the log of both sides, same way you would take the square root of both sides of an equation. So if we had x squared equals 4, we could square root both sides. We're going to take the log of both sides. Now, that handy rule that we just talked about a few minutes ago that said when we had log base b of x to the r, we could rewrite that as r log base b of x. So this exponent can come down from the exponent and kind of become a coefficient. So that's what we're going to do here. This negative 3x that is stuck in the exponent, we're going to bring it down and it's going to become a coefficient. So we're going to have negative 3x log of 2 equals log of 12. And all I need to do now is I need to isolate my x. So here's my variable. I need to get rid of this negative 3 and I need to get rid of that negative 2 or log 2. So what we're going to do is we're just going to divide it out since it's attached by multiplication. So we're going to divide by negative 3 and log 2, both sides, and we get x equals, I'm going to go ahead and bring this up front or out in front. We're going to have negative log 12 over 3 log 2. That's the exact answer. And then sometimes we want an approximate. And so the approximate you can get by just typing that into your calculator. And that approximate is 1.195. To type that into your calculator, you have to be a little bit careful. You want to make sure to use parentheses. So if I were typing this into my calculator, I would type negative log 12, close parentheses, divided by, and I need to have parentheses around that denominator. So we would have 3 log 2. You just have to be really careful to close parentheses appropriately and open them too. Let's do one more of those. This time we're trying to solve 7e to the x minus 8 equals 3. So this one's a little bit more complicated because we don't just have an exponential equals a number. We have this minus 3 and equals 3. So the first thing we're going to do is we're going to isolate the exponential. So just like we got x on one side with nothing else, we're going to get the exponential on one side with nothing else. So what I want to do is I want to move this 8 over here. So I'm going to add 8 to both sides. So I have 7e to the x equals 11. And then I'm going to divide by 7 to get just the e to the x all by itself. So I have e to the x is 11/7. Now, I have my exponential by itself, and my x is stuck in the exponent. Remember, my goal is to just get x equals some stuff. And x is currently stuck in the exponent, but what I can do is I can log both sides. And remember, we have those two main types of logs that we use, common log and natural log. And since natural log is log base e, and my base here is e, I'm going to use a natural log. So we are going to natural log both sides. This exponent here can come down in front. So I have x times natural log of e equals natural log of 11/7. And remember, natural log of e, this was just 1. So our solution here is x equals the natural log of 11/7. And the approximate value for that is 0.452. Now, it actually doesn't matter which type of log we choose. Our answer might end up looking a little different, but either way, it's still going to come out to the same value. That's all for this video. Thanks for watching.